So we're at a really interesting point where last time we started talking about the fundamental theorem of calculus. It puts the fun into calculus. And really what it's saying is there's this connection between this idea of integration and differentiation. So for reference, and it's probably good to write this down, we have the following fact. And so this is the first variation of the fundamental theorem of calculus. It says if I take the derivative from some constant up to x of a function f of t dt, then the output is f of x. So on the left-hand side, what are we doing? Well, we're first finding the total amount from c up to x. You can think of this as the accumulation function of little f. And this is creating a new function. And the derivative of this function is what we were finding the total for. So it somehow says, answering the questions, how much is the total accumulation changing? The answer is, well, what's the function? That's the answer. Okay, now at the very end, we were a little bit rushed, but we said, there's this really cool idea where you can take this and you can do a little bit of mixing with chain rule. So if you take the fundamental theorem of calculus and you mix it with the chain rule, you get the following. So I can take the derivative, but now instead of going from a constant up to x, I can go from some function, I'll say g of x up to h of x of f of t dt. And what you get is f at h of x times h prime of x minus f at g of x times g prime of x. So this is fundamental theorem of calculus plus chain rule. Now, which one do you remember? I like to remember both because oftentimes, depending upon the situation I'm in, I need to know the right rule. Definitely, you should understand this philosophy, and then if you need it, just say, okay, think chain rule, think chain rule. So here's a problem. Suppose we're given the following information. We know that the derivative of the following, the integral from x squared to e of t cubed f of t dt, is equal to 16 times x to the 17th. And we want to find f of t for t greater than or equal to 0. So it's not so obvious before we start that this is even possible, because our natural inclination is, well, somehow I first got to integrate. I don't know how to do that. Then I got to differentiate. At least I know how to do that. And it doesn't seem like it's going to be very good for us. But this is where the fundamental theorem of calculus really shines. Because the fundamental theorem of calculus says, look, if I need to take the derivative of an integral, there's a nice way to do that. So we're going to apply. And so in particular, we're going to apply this more general version. This is sometimes called, I think, Leibniz's variation. All right, so we apply this variation. So we still are going to have 16x to the 17th because we're not doing anything to this side. And what we're going to do is we're going to apply this variation of the fundamental theorem of calculus to the right-hand side. So we get that this will be, plug in the top, we could do it, e cubed f of e times the derivative of e, which is 0. So actually, anytime it's a constant, it'll always drop out. But the process still works. It's still a true statement. Subtract, okay, so now what do we have? Well, this is x squared. So what we do is everywhere where we see a t, we replace it by x squared. So x squared cubed f of x squared. And then we're going to multiply it by the derivative of x squared. So multiply that by 2x. And that has to equal 16x to the 17th. Well, okay, we clean it up a little bit. So we have the minus, there's a 2. So minus 2. And let's see, an x squared cubed becomes x to what power? 6. With another x, making it x to the 7th. F of x squared is equal to 16 x to the 17th. Well, now let's try to isolate f. So we're going to divide both sides by this negative 2x to the 7th. What happens when I divide 16 by negative 2? Negative 8. X to the 17th divided by x to the 7th? X to the 10th. Now I have the function f of x squared. What I'm after is the function f of t. You might say, aha, you're in trouble. How do you make x squared become t? Well, actually it's not so bad. What we can do is we can say, well, let's let x equal the square root of t. Now you'll notice we made a little assumption up here. We didn't draw much attention to, but now we will. We know t is greater than or equal to 0, so we can get away with this because the square root of t, that's no problem. So what does x squared become? X squared becomes t. So this becomes f of t is equal to negative 8 square root of t to the 10th. Well, what's another way to write square root of t to the 10th? T to the what power? 5th. And that's the answer. All right, so we can use the first fundamental theorem of calculus whenever we have something where there's an integral and a derivative involved simultaneously. But that's not the only version of the fundamental theorem of calculus. There's another variation, and so that's our thing we're going to start with today. So fundamental theorem of calculus, part 2, the return. And this is the one that we almost always use. And so when most people think of the fundamental theorem of calculus, this is what they're thinking of. And it says the following. Suppose I have this function, I'll say little f of x, and I want to compute the integral from a to b. In other words, what's the total from a to b of this f of x dx? Suppose we were able to find a new function, capital F. And capital F is the antiderivative of little f. Or put another way, capital F prime of x equals little f of x. Then here's the amazing thing, and it really is kind of amazing when you think about it. It says, if I want to know what the total is between a and b, and so this is asking what's happening over an interval, then I only need to know what capital F is at the endpoints. So instead of having to know the behavior over the whole interval, it's somehow encoded what's happening at these ends. Okay. So how do we get this? It's actually fairly straightforward because we know how to construct an antiderivative. So one way we can construct an antiderivative of little f is start with this cumulative function. So pick a value for c that makes sense for the problem. Just fix that. You go c to x of f of t dt. This is an antiderivative, and therefore if I have an antiderivative, any other antiderivative differs by a constant. So there's some constant out there. I'll just call it d for now. Now what do we do? Well, we're after the integral from a to b of f of x dx. And what we can do is we can break this integral into parts, c to b and a to c. And the key here is you'll notice that these match. These are both c. And because these are both c, I can really think of it as going just from a to b. All right, now what? Well, in the second integral, we flip it. So we can flip it the bounds. So instead of going a to c, we go c to a. But whenever you flip the bounds, that corresponds to flipping your orientation or reversing orientation. And whenever you change your orientation, you need to put a minus in. And this is going to be consistent. Calc 1, Calc 2, Calc 3, and beyond. So orientation matters. And now we say, aha, I actually know how to compute this. See, if I want to go from c to b, I come up here, I say put in x equals b. And what I get is that the integral from c to b of f of t dt, which is the same as f of x dx, the x is just a symbol. You can change it to be whatever you need. That would be capital F of b subtract d. So you get capital F of b subtract d. And for the same idea, this becomes capital F of a subtract d. And now the good news. See those constants, we don't know what that constant is, but we don't need to know. Because the minus d minus minus d cancels out. And you're left with just capital F of b minus capital F of a. And life is good. Life is good. So there's a couple of things we should think about. All right, now the first thing is, which antiderivative do we choose? Because we can find any antiderivative we want, because there's many of them, because you can always add a constant. And the answer is, well, we just find the simplest one. So usually what we do is we don't even bother with the plus c. In fact, we never write down plus c anymore. We'll always just choose it where the c is 0, because we just need to pick an antiderivative. Okay, now some notation. So we already know this notation for integration says find the total from a to b of f of x dx. So there's new notation to the output. It says, okay, find that antiderivative, we call it capital F of x. Then you have this vertical bar here. And that vertical bar, when you see that, you should think about that as indicating I'm doing an evaluation. We've seen it before. We use that same notation when we're saying, oh, take a derivative and do an evaluation at a particular value or at a particular point. So we're doing the same thing here. So this says evaluate, and then you see there's an a and b. And the nice thing is that it sort of implies an orientation, because there's like a top one and a bottom one. So it says plug the top thing into your function, f of b, subtract, plug the bottom thing into your function, f of a. All right. So what's the moral? Well, the moral is now the stuff that we did last week, where we had to do those limits of Riemann sums, and we're like, well, if we worked really hard, we got e to the x and x cubed. We kind of had to go on faith. Now, those problems are going to become very easy, because all we need to focus on is saying, let's find antiderivatives. There are a few cases where antiderivatives are still tough. And in those cases, we sometimes will look for other things. And one of those things that we might use is geometry. So, with all of this in mind, I think we're ready to move on. Any questions about the fundamental theorem of calculus, part 2? All right. Let's see it in action. So we'll do some good warm-up problems. Find the integral from 0 to 2 of 2x minus 3 dx. We can actually do this two different ways. So let's hopefully cross our fingers and get the same answer both times. Let's do it by first finding an antiderivative. All right. So if we were doing this by antiderivative, we would say, well, let's just find the antiderivative of each piece. Antiderivative of 2x, x squared. You can think of it as 2 times 1/2 x squared, and the 2 and the half cancel. Antiderivative of negative 3, negative 3x. And remember, when we're doing this definite integrals, we don't need to worry about the plus c. The plus c just cancels out anyway, so there's no need to worry about plus c. So there's our antiderivative, and then we put our bar that indicates evaluation, 0 to 2. So this becomes, plug in 2 squared is 4, minus 3 times 2 is minus 6, subtract 0 squared minus 3 times 0, which is 0. And the good news is, of course, the zeros are 0. 4 minus 6 is negative 2. Hopefully this doesn't feel very hard, because we don't want it to be hard. Our goal is to make life easier. So that's the good sign. Now I said we could do this in two ways. So this is using the technique, fundamental theorem of calculus, find an antiderivative, evaluate at the endpoints. This one we can also do by using some geometry. So what's this curve look like, 2x minus 3? It's a line. Can you tell me anything about this line? Intercept negative 3, slope is positive 2. So I come down to negative 3, and my slope is positive 2. In fact, I can come over here to 2, and I can see that when I plug 2 in, I'll be up at 1. And so I'm going to have that shape there. Okay. Now, what do we know? Well, the other thing we can figure out is, where do we have an intersection? So where's this point where I cross? Well, that'll be when 2x minus 3 equals 0, which is at x equals 3 halves. So 3 halves, or if you like, 1.5. Now, when we're looking for the total, this is one of those times when we have to remember that we're not just doing area, but we're doing our, again, quote mark area. And by that we say we're really going from the curve down to 0. Or, if we're below the axis, up to 0. So that means that there's really two pieces here. There's a triangle downstairs, which will be a negative area, and a triangle upstairs, which is a positive area. Now we can already see just from the picture that the downstairs triangle is bigger, so that our answer should be a negative number. That's a good sign. But we can go even further. So the area of a triangle, well, would be 1/2 base height. So for the first triangle, I can think of the base as being the width from 0 to 3 halves. So that would be, 1/2, not 1/3. 1/2 times 3 halves. So that's 1/2 times your base. And the height, I'll think of as -3. I could think of it as +3 and then just put a negative in there at some point. But okay, that's the first piece. And then the second piece, well, it'll be from 3 halves to 2. So I have 1/2 times another 1/2, that's the length, times 1. So if we multiply these together, you get -9/4 plus 1/4, which is -8/4, or -2. So it's consistent. That matches with what we think should happen. All right. Find the integral from 0 to pi of sine theta d theta. Now, are we okay with the fact that there's a theta here? Yeah. It's a symbol, and symbols can be changed to be whatever is convenient. In fact, the idea of changing symbols is the big idea that's coming on Friday. Spoiler alert, we're going to be changing what we call stuff. And it sounds really simple because it is. All right. Do we know something? Do we know the antiderivative of sine? Negative cosine. Yeah, see, like sine is like weird. Sine and cosine, they kind of flip behavior. So the derivative of sine is positive cosine, but the antiderivative of sine is negative cosine. We don't need our plus c because this is a definite integral. But we're going to evaluate from 0 to pi. Okay, so this is negative cosine of pi. Subtract negative cosine of 0. Well, minus minus means a plus. Cosine of 0, do we know what that is? It's 1. Cosine of pi? -1. So another minus minus 1 makes 1, plus another 1 gives us an answer of 2. Which tells us that if we look at the sine curve from 0 to pi, it goes up and comes down, that the area underneath this curve, y equals sine theta, this has area 2. Now, it's a really nice answer, but I don't think we could have done that geometrically, at least not very easily. So it's great to have these tools that help us to do these problems. Okay, let's try another one. All right. Find the integral from -1 to 1 of 1 over t squared plus 1. Now 1 over t squared plus 1, that's an interesting function. That's shown up on a quiz problem before. And if you look at that, it has this sort of behavior. As you head off towards infinity, it heads towards 0. It kind of peaks at 1. And so if we go from -1 to +1, it's like we're trying to find that area. I wonder what that could be. All right, well, let's think about it. Is there a nice antiderivative of 1 over t squared plus 1? Arctangent, yeah. Wow, what a great function. It's amazing. So this is arctangent of t. Then we evaluate -1, 1. All right, so arctangent of 1, subtract arctangent of -1. Well, do we know what arctangent of 1 is? It's pi over 4. Yeah, so when we're looking for the arctangent of 1, we're looking for some angle where the tangent of that angle gives us a value of 1. So the angle that does this is pi over 4. How about arctangent of negative 1? Do we know what that is? It's negative pi over 4. So we're going to subtract this term, negative pi over 4. And if we put these together, what do we get? 2 pi over 4, also known as pi over 2. So it's interesting because you look at this and you're like, that doesn't seem to have anything to do with pi. But amazingly, it turns out that pi is the answer. Well, pi over 2 is the answer, I should say. So sometimes pi shows up in rather unusual places. You see this a lot in statistics. Now, one thing you might have said, and we might as well do it right now, just point it out. Look at our shape here. Does it have any symmetry? What kind of symmetry do we have? There's a name for this. Even. It's even symmetry. And remember that the even symmetry means that there's reflection across the y-axis. And since we went from negative 1 to positive 1, another thing we could have done is we could have said, well, just go from 0 to 1 and double your answer. And that would have been the same answer in the end. It's not that much difference. The nice thing, of course, though, is then you don't have to remember what arctangent of negative 1 is. You just have to remember arctangent of 0. Okay. One more. Well, actually, there's even more still. But next one. Find the integral from 0 to 2 of the square root 4 minus x squared. Okay. Do we know the antiderivative of the square root of 4 minus x squared? It's not on one of our list of 8 things that we need to know the antiderivative for. So that's okay. Well, let's think about this curve. This feels familiar, like we've talked about this curve before. What kind of curve is this? It's a circle. Yeah, it's not just any curve. It's circulaceous. So it's the circle. What circle is it, by the way? What's the radius? 2. It's the circle radius 2. So I'm coming up here, and all right. Imagine that looked like a circle. All right. So what I can do is I can say, well, what I can interpret this integral as doing is I'm trying to find the total underneath this curve. So I can interpret this integral as saying I'm trying to find the area for this circle. Or rather, not the whole circle. How much of the circle do I need? 1/4 of it. So this is a place where we can use our geometry. So whenever you see this particular integral, and this shows up a lot more than you might think, mostly because it's one of the things we can actually do. So whenever you see that square root of some number minus something squared, you should be like, I wonder if this is like a circle going on here. So geometry tells us this is going to be 1/4 of the circle. Well, in fact, I'll just spell it out. The area of the circle of radius 2. So that will be 1/4 times pi, and then our radius is 2, so 2 squared. Giving us our final answer of pi. So that says that there's exactly pi sitting right there under that curve. All right, so far you can see that these are not so bad. Once you have this idea of antiderivatives, it handles a lot of problems. And then whenever we can't do antiderivatives, we can step in with geometry. But there are shortcomings, and you got to be cognizant. Got to be aware that things can go bad. So this is a sort of a note just to be careful. So you can read the following, or I'll just explain it to you. One of the things you might encounter is you might have functions which are not continuous. So by that, what do we mean? Well, we'll come back to you, integral. You might have a function which has something like this type of behavior, where maybe it's horizontal, then it jumps down and becomes like a circle, and then Then all of a sudden it jumps up here and it's a line. And so in other words, you have piecewise functions. So here's the good news. These kinds of discontinuities, which are the ones you might remember we call these jump discontinuities, where you can basically say from the you're drawing with a pen or a pencil and you lift up, you move up or down and you put it back down again and keep drawing. These are actually not bad. And the way we handle this is you handle this piecewise. So in other words, when you're doing integration, we do integration piece by piece. So if I were asked to find a total of this, say, between, I don't know, here's A and here's B, do integration, whoops, I probably should not try to write and talk at the same time. What you do is you say, look, let me just break it up into 3 parts. And you say, I find this area, I define this area, and I find that area. And then you just add them together. Life is good, you're okay. So for anything where you have a discontinuity which is not so bad, no worries. Just do it as you normally do. But bad things can happen when you have other types of discontinuity. And sort of the classic example is when you have things blowing up to infinity. So to try to convince you that, yes, be aware bad things can happen when you don't have continuity, we want to do this one integral really quickly. So let's just pretend like life is good. It's a warm summer day. Well, it's a warm fall day. Well, it's a fall day. All right. Suppose we were asked to integrate this, and in our naivete, we were like, well, that's not so bad. Because we're doing calculus, what would we do with 1 over x squared? What does 1 over x squared become when we're doing calculus problems? X to the negative 2. Because you really want to have x to a power. So x to the negative 2. The reason why you want to have x to a power is that's the way that the rule is phrased. So you say, okay, well, that's not so bad. The way we handle that, what's the rule? Well, the rule is add 1 to the exponent. So it's x to what power? Negative 1. Then you divide by the new. So we're going to divide by 1 over minus 1, so it'll become minus 1. And then we're going to evaluate from negative 1 to positive 1. So again, this is negative 1 over x evaluated from negative 1 to positive 1. So we plug these in. So this is negative 1 over 1, subtract, and then we have negative 1 over negative 1. Okay, so there's a lot of negatives going on here. Already you're feeling there's a lot of negativity coming from this problem. Well, but if you work it out, these two negatives cancel. You end up with minus 1, which is minus 2. And I'm not going to box that, but I'll say, okay, that would be your answer. And a lot of people would just move on and not even think about this. But we're not a lot of people. We like to think. Should negative 2 concern us? Because we've had negative answers before. In fact, we've had negative 2 as an answer before, today. And we're like, yeah, that's no problem. But let's think about what's going on here. Let's actually sketch 1 over x squared. And think if negative 2 seems like a reasonable answer. Well, if you sketch 1 over x squared, what happens is it does this. Because regardless of which side you come from, when you square it, it's always going to be positive. So if I'm getting close to 0, I have 1 over a very small positive number, which means I'm blowing up to a huge positive number. So from both sides, I'm approaching positive infinity. Now, let's think about this. What we're saying is we're going from negative 1 up to positive 1, and we're finding the total, and the total should be what? It looks like it should be a positive value, because everything is positive. So somehow we found a total that was positive, and yet our answer was negative 2. Well, unfortunately, we don't have all the tools to resolve this problem. We will have to wait until Calculus 2 to see how to fix this, and there are ways to fix this. And it turns out that what's happening here is that this area is actually infinite. And now you're thinking, cool, we just proved that negative 2 is infinity. No. That's not what we proved. What this shows you is just there's a danger. So be aware of the dangers. And the good news is we will not try to trick you on the test. We're not going to ask you to do any integral where you can't do it. Integrals will work out nicely for you. All right, well, now an application. And it's an application that we've already been talking about, so let's just make it explicit. We've been talking about area where we put quote marks. Now we're going to take off the quote marks. True area. So I really, truly want to find area between curves. So I have two curves. One curve, say, on the bottom, y equals f of x. Another curve on the top, y equals g of x. And I have a starting point, a and b. And I want to say, what's the total area? So you can see it's this part that's shaded here. How much area is in that region? And the answer is, you integrate from a to b, g of x minus f of x dx. Now this is our first sort of foray into applications of integration. And you're going to see this a lot in next semester when we do Calculus 2. So it's good to understand what's happening, the idea of integration. So the idea of integration is always the same. We're looking for something. So what we're going to do is take what we're looking for, and we're going to break it up into small parts. And each part is going to be easy for us to understand. We're going to figure out what that part is, and then we're going to add all the parts back up, and life is good. Now for us, we're after area. So what we're going to do is we're going to break our region up into small parts, where each part is a little tiny area. We're going to figure out the area of that little part, then we're going to add it back up, and that's going to give us our total area. So the way we do it is we slice things up. So, for example, from here, I can think of taking a small little slice. And I want to ask the question, how much area is in that slice? Well, if I have a very small slice, I can really think of it as a very thin, very tall rectangle. And I say, all right, if I think of it as a thin, tall rectangle, there's two dimensions to my rectangle, a height and a width. What's the height? Well, the height is the distance between the two curves. So this g of x minus f of x, that's the height of the rectangle. What's the width? Well, it's this really teeny tiny change in x. That's your dx. That's your width. So what's happening is when you take g of x minus f of x times your dx, that is the area of one of your little tiny pieces. And then what you do? You add them all up. So you really should think of anytime you see an integral is like I'm adding up a lot of little parts. And I just have to understand what each little part is doing. Now there's some other notes down here on the bottom to keep in mind. We're looking for area between curves. It's possible that the curves can cross each other. If they ever cross, what happens is that the curves need to change roles. The top has become the bottom has become the top. So how do you handle that? And the answer is break it up into separate integrals. Handle them separately, put them all together to get your final answer. So let's do some problems. So our first problem. Find the area between y equals x squared and y equals x plus 6. And already you can say, wait a second, you forgot something. You have the two functions, but you've actually forgotten two things. One, you haven't told us where to go between a and b, and it hasn't told us which one's the top one. So if we ever say just find the area between the curves, well, that means that we get to find where they intersect. So if there's no a and b given, figure out where things intersect. Well, how do you find out when things intersect? Yeah, so the way to find out if things intersect, or rather when they intersect, is we set the functions equal. So let's do the intersection. So we would set x squared needs to be x plus 6, So now we rearrange. That's the same as saying x squared minus x minus 6 equals 0. And if we're lucky, what should be true? It should factor. Well, are we lucky? Does it factor? He asks as he writes it down like it's going to factor. It probably will. Well, someone has said 2 and 3. Is it? But which way 2 and 3? Minus 3 and plus 2. You can check, right? Because you get the x squared plus 2x minus 3x is minus x and minus 6. So where do the intersection points happen? At 3 and negative 2. So in particular, this negative 2, that's the smaller value, so that's A, and 3 is the larger value, that's B. So I'm going between negative 2 up to 3. Now I have the two curves, and the question is, which curve is on top? Now there's a couple things you can do. One thing you can do is you could sketch the curves and try to get an understanding. These aren't hard to sketch. For example, y equals x squared. That's a parabola. We've seen that. How about y equals x plus 6? It's a line. Slope is 1. Y-intercept is 6. So it's doing something like that. And so then we say, okay, so if there's our intersection points, negative 2 and positive 3, which one's on top? X plus 6 is the one on top. So we see, okay, so we're going from x squared less than or equal to x plus 6. Now, suppose you didn't sketch it, or maybe for some reason you couldn't figure out how to sketch these curves. What could you do? The answer is, well, I just need to know which one is on top at any point in the middle. So I could pick a point, convenient point between negative 2 and 3. What's the convenient point between negative 2 and 3? 3 halves? I was thinking 0, but okay, let's plug in 0. If you plug in 0, you can say, okay, in the parabola I'd be at 0, and the line would be at 6. The line is bigger. So the 6 would be the one on the top. So that's another way to tell if you don't know how to graph it. So now we're ready to go. We know where we're going from. We know which one's on the top. So we can do the integral from a to b of the top, x plus 6, minus the bottom, minus x squared dx. Oh, whoops, sorry. I should have written negative 2 and positive 3 for a and b. Okay, so let's finish this. Antiderivative of x. Half x squared. Antiderivative of 6. 6x. Antiderivative of minus x squared. Minus 1/3 x cubed. And we're going to evaluate from negative 2 to positive 3. So we get what? Well, plug in 3, you get a half times 9, which is 9 halves. 6 times 3, which is 18. Minus 1/3 times 3 cubed, which is negative 9. Because you can think of it, 3 cubed, there's 3 3's, but there's also a 1/3. So you get rid of one of your 3's. So it's 3 squared. All right, then we're going to subtract. Plug in negative 2. So negative 2 squared was before, times a half would be 2. And then 6 times negative 2 is negative 12. And negative 1/3 times negative 2 cubed would be plus 8/3. Now, I'm going to point out something which is really cool. So this is something which has saved a lot of points in my life. We call these parentheses. And parentheses help. So because the thing is, you're plugging at the top, subtract, plugging in the bottom. And if you forget that parentheses, you might think, oh, I only need to subtract the 2. But remember, you have to put that negative all the way through into all the terms. So, what did we get? Well, 9 over 2. And the 18 minus 9 we can combine. So that will be plus 9. 2 minus 12 is minus 10, but we're subtracting it, so that's a plus 10. And then we have a minus 8/3. Now, if we wanted to, we could put this all over a common denominator of 6. And apparently I want to because I keep writing stuff. So that would be 27. And I think the reason I'm doing this is just because I want to point something else out here at the end. 19 times 6 is a big number, 114. Is that 19 times 6? We'll say that's 19 times 6, and then we're going to subtract 16. And if you do all this, you should end up with another number, I think 125 over 6. Is that close enough? Okay. The moral here is that number is positive, which is a good sign. If we had gone to negative, what do you do? Now, I'll tell you what a lot of people do. They just like, yeah, just put a positive here. Usually if you have a negative, what does that mean happened? You switched whatever top and bottom. Or maybe you have your endpoints, where do you integrate, are in the wrong location. So if you have a negative, don't just erase it. Actually figure out what happened and then fix it. So, but this is at least a positive number. I hope it's right. It's close enough. I'd get partial credit for that. That's all we need, right? Partial credit. That's good enough. Okay. Find the area in the first quadrant bounded by y equals root x and y equals x minus 2. Simplify your answer. Okay. Let's sketch that. So y equals square root of x. That's not so bad. We've seen that kind of curve before. It looks something like that. Y equals x minus 2. What does that look like? It's a line. It's slope, intercept at negative 2, and then it has a slope of 1. So it actually crosses the axis at positive 2, and it has a slope of 1, and does that. So I have this line, y equals x minus 2. Now, it would probably be convenient to know where do these two lines cross. Now, we can do a couple of things. We can definitely do the following. We can set square root of x equal x minus 2 and solve. But one of the things we can do is always guess. Guessing is perfectly allowed. We just have to check our answer. Is there a reasonable guess? Because usually you should suspect it should be a nice number to work with. So it's not going to be 1. So the next thing that has a nice square root is 4. Then we check. Square root of 4 is 2, which is equal to 4 minus 2. So yes. So this is at 4. Okay. So remember, we want to be in the first quadrant. So we're not going to go down below. That's why I only drew the line in the first quadrant. So this is our area we want to find. Now, as you look at this, you might say, okay, what needs to happen? Well, there's a catch. We're still going to do top minus bottom, but as we're moving along here, top minus bottom, top minus bottom, top minus bottom, something happens here at 2. What happens? The bottom curve changes. It's no longer the axis. So there's a change in behavior. So how do we handle that? The answer is we do it twice. Or rather, we do 2 integrals. So we're going to have one part from 0 to 2, and then a second part from 2 to 4. And the reason we're doing that is that the bottom is going to have different curves depending upon which part we're in. So anytime you have a change in the curve, you've got to split the integral. So we're going to have the integral from 0 to 2. In this region, what's the top curve? Square root of x. And in calculus, we write that as x to 1/2. Then we're going to subtract the bottom curve, which is 0. Then in the second part, which goes from 2 to 4, our top curve will be x to 1/2 still. And then we're going to subtract our bottom curve, which is x minus 2. And again, I'm going to point out, check it out, parentheses, good stuff, good stuff. You're going to save points if you use them. And you want to get all the points. All the points. That's what you want. Okay, well this isn't so bad. What's the integral of x to 1/2? Well, you would add 1 to the exponent, which gives you 3 halves, and then you multiply by 2/3. So remember, whatever it is, you add 1 to the exponent, then you divide by the exponent, or you multiply by the reciprocal. So if it's 3 halves, you flip that over 2/3. And we're going to evaluate that from 0 to 2. And then whatever that is, we're going to add to it. Okay, integral of x to 1/2 is still 2/3 x to the 3 halves, which is no surprise. Then I have minus x, which is minus 1/2 x squared. Then I have plus 2, which is plus 2x. I'm going to evaluate that from 2 to 4. So we plug the numbers in. We get 2/3 times 2 to the 3 halves. And 2 to the 3 halves is, I guess, something we'll have to live with for now. Plus, now we come in here. 2/3 times 4 to the 3 halves. Well, that one I think we can do. If I want to do 4 to the 3 halves, I can do square root of 4 first, which would be 2. Cube it, 8. So 4 to the 3 halves is 8. Times 2/3 gives 16/3. Minus 1/2 times 4 squared. So that's minus 1/2 of 16, which is minus 8. Then we have plus 2 times 4, which is plus 8. Okay? So that's plug in 4. Then we're going to subtract. We plug in 2. We're going to get 2/3 times 2 to the 3 halves, which, well, I guess we'll just live with for now. Minus 1/2 times 2 squared. Would be minus 2, because it'll be minus 1/2 times 4. And 2 times 2 is plus 4. Okay, so now we start noticing that some nice things have happened. We get some cancellation. The 8's cancel. Anything else? Yeah, the 2/3 times 2 to the 3 halves actually cancels. Well, that's really nice. What's left? Well, we have a 16/3 here. And then here we have a 2, minus 2 plus 4, but that's being subtracted. So it becomes minus 2. Or you get 16/3 minus 6/3, which is 10/3. Now, we can do area in a different way. Now, what we just did here is we said, you know, let's think about breaking things up into rectangles where we have little tiny rectangles up and down. But what else could we have done? We can do little tiny rectangles left and right. Okay? So I'm breaking it up. So how do we do that? Well, what we do is we integrate the right hand minus the left hand. So right minus left is width. The dy is the height. So height here is dy. So it's really breaking things up into little rectangles and adding them up. Same question, integral with respect to y. So how many different integrals are we going to need if we integrate with respect to y? We need 1, because we always have the same right-hand curve and same left-hand curve. So it's just one integral. Now we need to know a few other things. Well, we know where this point's at, because this is where we intersect. If x equals 4, y is 2. So where does y go from? Y goes from 0 to 2. And now we need to know, well, what's the right-hand curve? Well, you might say it's y equals x minus 2, but I need to have it as x equals something. X equals y plus 2. And then I'm going to subtract this left-hand curve. So this is x equals y squared and dy. So right minus left is the width, dy is the height. And it might not surprise you, if you were to integrate this out, you will see that it's not so bad. For one thing, it's only one integral. And you plug in 0 and 2. 0 is really nice, because if you plug in 0, what do you get? You get 0. So what do we end up with? We get 1/2 times 2 squared, which is 2, plus 2 times 2, which is 4, minus 1/3 times 2 cubed, which is 8/3. And now you're looking like, ha, Steve, it's not the same. Or is it? 6 is 18/3 minus 8/3, it's 10/3. Of course it's the same. It's the same area, just found in a different way. Okay, let's try some more problems. Find the area bounded by y equals 2 sine x and y equals secant x tangent x between x equals 0 and the smallest x positive where the two curves intersect. Now, y equals 2 sine x, that's not so hard to draw. I mean, that looks something like 2 sine x, looks like sine x going up. Secant of x, tangent of x, well, at 0, it's 0, and then it should be blowing up as we get close to pi halves, so it should be getting big. So there's some place where they cross. Okay. So we're looking for this sort of piece right here. Now, we're going to verify that we're not just crazy. In other words, that what we think is on top is on top. But first we've got to figure out, where are these crossing? So we do what we would do in any problem where it says, all right, if I now want to know the area between curves, I got to find the intersection. If I need the intersection, I set things equal. So 2 sine x equals secant of x tangent of x. Now, if you don't know anything else to do, write everything in terms of sines and cosines. So 1 over cosine of x, and tangent of x is sine x over cosine of x. We know x is going to be positive, and so it's not at x equals 0, because at x equals 0 they do intersect. So we cancel off a sign. So we get that this is going to happen when 2 is 1 over cosine squared of x. Well, flip both sides. Cosine squared x should equal 1/2, which means cosine of x is the square root of 1/2. Well, where does that happen? When does cosine of x equal square root of 1/2? That's actually a really familiar angle. Another way to write square root of 1/2, by the way, this might help, is square root of 2 over 2. And that happens at pi over 4. Okay, so now we know where the intersection is. It's going to happen at pi over 4. Now, how do we know that our picture is right? In other words, how do we know that it's the 2 sine x is up here, whereas the secant of x tangent of x is down here? And the thing is, we're not 100% sure yet, so could be wrong. So let's figure that out. So we think, okay, is there a convenient angle between 0 and pi fourths? Pi 6 is pretty convenient. So 2 sine of pi over 6. Now it turns out that sine of pi over 6, it's actually a nice value. That's 1/2. So you get 2 times 1/2, which is 1. Now, secant of pi over 6, tangent pi over 6. Now, that's maybe a little bit harder, but remember we can do the same thing we did here. That's the same as sine of pi over 6 divided by cosine squared of pi over 6. Well, sine of pi over 6, it's still 1/2. That hasn't changed. Cosine of pi over 6 is square root of 3 over 2. So this is, when you square it, becomes a 3 over 4. So if you take that 3 over 4 and you flip it, what do you get? Well, you get 1/2 times 4/3, which is 2/3. And yes, 2/3 is smaller than 1, which means our picture's accurate. So actually now we have everything we need. We understand which one's on top. We understand where we need to go from. So our area is going to be equal to the integral from 0 to pi over 4 of 2 sine of x, which is the top curve, minus secant of x, tangent of x, which is the bottom curve, dx. Well, what's the integral of sine? We've done that. That's negative cosine. So minus 2 cosine of x. Integral of secant x tangent of x, that's secant. So minus 2 cosine of x minus secant of x. Evaluate from 0 to pi over 4. Now, cosine of pi over 4, well, that's where we got the square root of 2 over 2 from. And then we're multiplying it by 2, so that's going to be minus square root of 2. Secant of pi over 4, well, it turns out that to find secant of pi over 4, you take cosine of pi over 4 and you flip it. So instead of square root of a half, flip a half, it's square root of 2. So that's also minus root 2. That's looking pretty negative, and we're about to subtract something. That's all right. Maybe we'll subtract something which is positive. Plug in 0. Cosine of 0 is 1. So you get minus 2. Secant of 0, also 1. So you get minus 1. So this becomes negative 3, but we're subtracting that. So that makes it positive 3. And then we have minus 2 square root of 2. And it does turn out square root of 2 times 2 is less than 3. A positive number, not by much, but you don't have to be by much. We just need to be positive to make sense. And you see, it's kind of a small sliver, so we probably wouldn't expect a big number. And there we go. That's the area. Well, we have space. Let's see if we can do one more. Find the area bounded by the curves y equals x cubed and y equals x squared plus 2x. So to figure this out, we need to figure out where these curves intersect. So, where does x cubed equal x squared plus 2x? Move everything across. X cubed minus x squared minus 2x equals 0. And hey, everything has an x. That makes life good. We pull that out. Now, x is fine. That's good. Can we factor x squared minus x minus 2? Of course we can. Come on. By now, we've done that before. That's x minus 2 times x plus 1. And you can check. You get x squared plus x minus 2x is the minus x and minus 2. So they intersect at 3 locations, at 0, at 2, and at negative 1. Now what does that mean? Well, it means that our shape is going to be a little bit more interesting than maybe we were hoping for. Because what's happening here? The y equals x cubed, that's the cubic function, and we've seen it before, and it comes up, it levels off, and goes up again. So this is y equals x cubed. X squared plus 2x is a parabola. We know it opens up because it's positive. We also know where the intersection points are on the axis. So where do I hit the y-axis? Or sorry, where does I hit the x-axis? When does y equal 0? The answer is I hit it at 0 and at negative 2. And so what I get is I get a parabola that comes down and then comes up again. And then, okay, my picture is not very good. What happens though in the long run is that a cubic beats a quadratic. So what's going on? I have actually 2 pieces here. I have a piece here and a piece here. So, namely, I have where I go in between these various intersection points. So there's a negative 1, a 0, and up here is a 2. Now, what's on top, what's on the bottom? You can always just test. So for instance, suppose I pick a number between negative 1 and 0, say negative a half. If I plug in negative half here, I'd get negative an eighth, which is pretty small. If I plug negative a half here, I would get 1/4, and then I get minus 1, which is negative 3/4. So in this part right here, the first part, I have that it's x cubed on top and x squared plus 2, top. X squared plus 2x is on the bottom. But in this second part, well, let's pick 1. If I put in 1, 1 cubed is 1, versus 1 plus 2, which is 3, which means they change roles. It's x squared plus 2x on the top, and then it's x cubed on the bottom. So, what do we need to do this? Well, the answer is we have to split it into two parts again. So anytime I get change in behavior, I have to split into two parts. Now you might say, wait a second, couldn't we just do one integral, negative 1 to 2 of top minus bottom? You could do that integral, but you would get the wrong answer. The reason you get the wrong answer is because you switch top and bottom, you might say, oh, this part would end up becoming a negative contribution. So you'd get a little bit of cancellation out here, so you wouldn't actually be finding the proper area between the curves. So, here we go, our setup. We're going to go integral negative 1 to 0 of x cubed minus x squared plus 2x. That finds our first piece plus integral 0 to 2 of x squared plus 2x minus x cubed. That finds our second. So we go through, we do our computation here. This will be 1/4 x to the fourth minus x squared, gets us minus 1/3 x cubed, and then minus 2x, and the integral of that is minus x squared. We're going to evaluate that from negative 1 to 0 here. It's actually going to look really familiar. It's essentially the same thing, it's just going to have all the signs flipped. So you get 1/3 x cubed, and you get x squared, and you get a minus 1/4 x to the fourth, but now 0 to 2. When we plug in 0 here, we're going to get 0, then we're going to subtract, plug in negative 1. Well, negative 1 to the fourth is 1, so you get 1/4. Negative 1 to the cubed is negative 1, so there'd be a minus and another minus, so that'll be plus 1/3. And negative 1 squared is just negative 1, so we have to subtract 1. Plus, come over here, put in 2, we get 2 cubed times a third, which is 8/3, plus 2 squared, which is 4, then minus 1/4 times 2 to the fourth. Well, 2 to the fourth is 16, times the fourth is minus 4. Well, those cancel. That's very convenient. And so what do we have? Well, we have this 8/3, and then we have this other stuff. Well, what is this other stuff? It's minus 1/4, minus 1/3, plus 1, and then plus 8/3. So it looks like common denominator will be 12. So what do we end up with? Here we get minus 3 over 12, minus 4 over 12, plus 12 over 12, plus 32 over 12. Because that multiplied by 4 times 8 is 32, 12 over 12. All right, well that's 44. Subtract 4 is 40. Subtract 3 more will get us to 37. 37 over 12. And that's our total area. And there you go. And that's it. And you can now do lots of problems. Area. Find the top, find the bottom, find the intersection points if you need to, and be careful. There will be a couple problems where sometimes you have to break things up, and of course, sometimes you don't. All right. See you next time. Bye.